Hey everybody, today in Transformations lesson number 5, we are going to learn about something that, unlike the other lessons, is not, okay, we don't have to capitalize it, but it's all good, not a rigid motion. Today we are working with dilations. Now, I don't really know why people always say dilation as if somehow there's an extra A in it. It's just dilations. I don't know why the habit is to add an extra letter there, but dilations. And dilations are not isometries. Now, we're going to practice this 3 different ways. Okay, we're going to practice it about the origin, about a point on your figure, and about a point just randomly out in outer space. So here's what we're going to do. We're going to start by trying to dilate a figure about the origin. So we're going to take a triangle here, -2, -1, 2, -2, and 1, 2. And that's the one we're going to start with. Okay, so let's connect these. So the first thing we're going to do is practice dilating about the origin. So we'll give this a little bit of a label here really quick. Now, what you see here, if you look at the math code, it's a dilation with a scale factor of 3, and it's about the origin. So we've seen that before, that O, that zero-ish looking thing. We know that that's the origin that we're going to dilate about. Anytime you have a scale factor greater than 1, it is considered an enlargement. So anytime the scale factor is greater than 1, it is an enlargement. Now, when you are dilating with a scale factor of more than 1, your figure should get bigger, which means in this case, all you have to do is take the distance that you are from the origin and multiply it by 3. So if we were dilating point C, instead of being in its original spot, it would have worked its way all the way up here. Okay, now we can use that exact same logic with point B. Instead of being at 2, -2, we're going to triple that distance, and it's now going to be at 6, -6. Now, this is usually where a lot of people look, and they're like, well, can't I just take the ordered pair and multiply the ordered pair by 3? Absolutely. In the case of dilations, you can if you are dilating about the origin. You can just take whatever your ordered pair is, and you can multiply your ordered pair by the scale factor and get your new one. So instead of -2, -1, we're going to triple both of those numbers, and we are now going to get -6, -3. If you drew it correctly, you should get a picture of a figure. Now, we'll get to this more in the area chapter, but the side lengths are now going to be 3 times bigger. And actually, it turns out the area is going to be 9 times bigger. But I don't really want to get into why that is right this second. I just want to kind of give you an idea of what's going on here. Okay, so now we have a figure. The side lengths have each tripled. The area has actually increased by 9. You're dealing with a way bigger figure than you once did. Now, in the case of your other one here, a dilation with a scale factor of 1/2, now you're dealing with a scale factor less than 1, which means instead of an enlargement, it is a reduction. So now you are going to take every ordered pair and you are going to cut it in half, which means instead of -2 and -1, you're going to get -1 and -1/2. Instead of 1, 2, you're going to get 1/2 and 1. So again, we are taking every ordered pair and we are multiplying it by 1/2. With B, instead of the point 2, -2, now we're going to go to 1, -1. That one might be a little bit easier to deal with because of the way the numbers work out. But now, hopefully, what you're noticing in this whole deal is that now the side lengths have been cut in half. It's a little bit harder to see. That's why I'm zooming in on that. So again, just to review, if the scale factor is 3, let's say, like we did in our original, we went from -2, -1 to -6, -3 because we multiplied every ordered pair, every value in the ordered pair by 3. But if we are dealing with a scale factor of 1/2, we are now going from -2, -1 to -1, -1/2. So that's the difference. Okay. So I'll zoom out. You can kind of get the big picture here. And you do that for every ordered pair. Okay, so we have the doubled side, the tripled side lengths, not doubled, I'm sorry. They were the tripled side lengths, and then we have the side lengths that were cut in half. All right. Now we're going to try this idea again, but this time we are going to try a different type of dilation. So we're going to have the point. Let's start with -3, -3, 2, 1, and -3, 2. Okay, now I like this example a lot. It's going to look different because it is a different type of dilation, and I'm going to show you why here in just a second. All right, so we have our new A, our new B, and our new C. Now, what you'll notice that's different about this is it is a dilation with a scale factor of 2, but this time, instead of being about the origin, it is about point A. Now, the way I think of this, point A becomes your anchor. As in, if you're on a boat and you anchor the boat, that means you're putting the boat down in that spot. Point A is going to be anchored. Everything else is going to expand around it, but point A is going to stay the same. So again, A prime is going to be exactly where A is. A is not going to move. Okay, so A prime is going to stay. It's the other two that are going to stretch to accommodate it. So again, if you have a scale factor of 2, that means the side length is going to be twice as big. So basically, how far away is A from C right now? 1, 2, 3, 4, 5. Well, double that would be 10. So now the distance that A has to be from C is going to double. It is now going to be 10 units away. Now you're going to do the same thing with point B. Right now, to get from A to B, you have to go up 4 and over 5. So now you need to go up 8 and over 10. You have to double that distance to get to your new point B. So again, A will stay the same, B and C will expand so that they can be twice as far apart. Now, if we did a dilation with a scale factor of 1/2, again, the technique will be the same. A prime will be the same. B and C will anchor, but because the scale factor is only 1/2, that means my distance away is going to be cut in half. So instead of being 5 units away, it's going to be 2.5 units away. And instead of up 4 over 5, we're going to go up 2 and over 2.5. So it's going to look something like that. So we'll zoom in again because I think we've got a lot going on here. If we are getting bigger, then we're going to be farther away from our initial point. If we are getting smaller, then we are going to be closer to our original point. Okay, so this one has the scale factor of 2. This is our original, and this has the scale factor of 1/2. Okay. All right. Now, if you want the big time, awesome 3D image, by the way, freeze that if you need to. If you want the awesome 3D image, we're going to make a rectangle for this last one. And we are going to go with -5, 2 would be right there. 0, 2 would be right there. 0, 0, so we'll go to the origin. -5, 0 would be right there. So as you can pretty much see, we are going to deal with a rectangle for our final dilation. Now, the difference here is that this time, when we do our dilation, we are not going to dilate about the origin, and we are not going to dilate about a point that is already on our figure. We are going to dilate about some random point in outer space, which I just decided to call point Q. Don't know why I chose Q. It quite frankly doesn't matter. Now, a dilation with a scale factor of 2 about point Q means whatever distance you were away from point Q is going to double. So right now, point A is currently down 5 and to the right 2 from Q. So if we want to double that distance, we are now going to be right there. That will be my new point A. Now, all the rules about scale factors still apply. My new figure is going to be twice as big as the old one. Even if you don't know it yet, it will be. Just watch how it develops. From Q to D, right now we are down 7 over 2. So now we're going to have to go down 14 over 4. We are going to have to double that distance. And that's going to put my new point D, that's going to be D prime. I'll move it over so I have room to put the mark. My new D prime is going to be all the way down there. All right, take a look here from Q to B, down 5 over 7. So if I were to keep it going down 5 over 7 again, that is going to put me all the way over here. And then last but not least, we're going to go Q to C. Now, if we go all the way across to the origin, and then we just keep going double that distance, that's going to be right about there. My new C prime is going to be right there. So if you take a look at what happened to our new rectangle, our side lengths did double. Maybe not quite the way we expected to. I actually think that's a really cool 3D image we've got going here. It ends up looking something like that. Now, one last example that you need to try. We're going to try the dilation of 1/2, a scale factor of 1/2, and we're going to do it about point Q. So now the distance that we are away from point Q is going to get cut in half. So one last time, currently point A is down 5 over 2. So we're going to go down 2.5 over 1. Currently, point D is down 7 over 2. So I'm going to go down 3.5 and over 1. It's going to look a little bit sloppy here because we are zoomed way in. As soon as we zoom out, I think the big picture will look a lot better. Point B is currently down 5/7. So I'm going to cut those numbers in half, and I'm going to go down 2.5/3.5. Those are both odd numbers, so that's why it's going to be a little bit hard to deal with. You're just sketching it the very best you can. And then last but not least, point C is currently down 7/7. Now we're going to go down 3.5/3.5. And again, it looks really sloppy right now, but as soon as you make the rectangle, it begins to make a lot more sense. It begins to become a lot more clear. And I think, again, if you zoom out, it's going to look a lot better as well, because now you can see the big picture. You can see that this is the one that has the side lengths that are double the original. This is the original. And then this is the one that has side lengths that are half as long. All right, I hope that helped you out. Helps you understand dilations a little bit. Remember, this is the only one where the side lengths actually change. So that's why it makes it different. We got to pay attention to that. I hope this helps. Thanks for watching. I will see you next time.